So thank you very much I'm very happy to talk and present my result here. So the title of my talk is Matrix Realization of Homogeneous Hessian Domains. So Hessian domain is a subclass of statistical manifold. It is the classical and basic object in information geometry. And I mainly consider the homogeneous Hessian domain, so which means that a Lie group acts on this domain as an automorphism group transitively. So in general, so homogeneous space is a very nice property in many sense because of its plenty of symmetry. And here, my result is that I realize every homogeneous Hessian domain as a set of matrices. So you can treat nice examples of Hessian domain just using linear algebra, not without knowing Lie group nor Lie algebra. This is my result. So here is the plan of my talk, and instead of stating the full statement of my result, I like to show you the example of two-dimensional Hessian domain, how it is realized in my tool. Then the detail for the detail, please see the proceedings, but I'm sorry that the formulation is slightly different from the proceedings, so I'm sorry for this inconvenience. Okay, so what is Hessian domain? So let D be a domain in a real vector space, and G a Riemann metric, which is expressed as locally for each x point x. There exists a neighborhood of x. Then, so G over the restriction of G is expressed as a Hessian of some functions. So Hessian metric is locally expressed as a Hessian of some functions. And I call the pair D and G a Hessian domain. And this is often appears in information geometry, you know. And typically, this is the parameter space of exponential family of probability distributions has naturally such a Hessian domain structure. The domain is realized in the so-called E-coordinate, and the metric is given as the Fisher metric. And we say that the two Hessian domains, dg and d prime, g prime, are isomorphic if there exists a transform phi, which is a affine transformation, which maps the domain and the metric. And the automorphism group of a Hessian domain is defined as a group of all affine transformations which preserves the domain and which preserves the metric. And we say that the Hessian domain is homogeneous if the automorphism group acts on the domain D transitively, namely for any 2 points in the domain. So this is for any 2 points in D, there exists a automorphism group which maps X to Y. And such a homogeneous Hessian domain is studied by Hirohiko Shima in 1980. So he established a very wonderful theory for homogeneous Hessian domain. And here is one of his results is follows. So every homogeneous Hessian domain is convex. So there exists only a global potential which expresses this homogeneous domain as a Hessian matrix. So here's the example of homogeneous Hessian domain. So first is very simple. So D is just a Riemann vector space, and G is just a standard inner product. It does not depend on the position. And the potential of this standard inner product is just this quadratic form. And then the second derivative of this Hessian of this P gives the standard inner product. And it is very obvious that this metric G, in this case, is invariant under the translations. But we can verify the invariance by observing this potential function. Because potential function is not invariant under translation, but the difference of the functions are just linear affine functions. Since the difference is linear affine linear, since the difference of potential function is affine function, then taking the Hessian, we have the invariance of the metric. And this example comes from, so in my perspective, this is a parameter space of the normal distributions, which is a very covariance matrix is fixed identity, and the mean varies. Then, so this family of distribution has this exactly this structure. In second example is positive definite. So I denote omega n. This is a set of positive definite symmetric matrix, which forms a convex cone in the vector space of symmetric matrices. And for parameter S positive, define GS is S times somehow standard Riemannian metric on this omega n, and phi s, this S times this log determinant. So GS, phi s is the potential of GS. And the metric GS is invariant and not invariant under the translation, but invariant under this multiplying A and transpose A from left and right. And then indeed we can check the invariance directly from this expression, but of course also we can check the invariance by observing the potential function. This potential function is not invariant, but under the row A, but invariant and up to the constant difference. So taking a Hessian matrix, we have an invariant of the metric. And actually, so the group of this Hessian domain consists of such row A transformations, and this acts on omega n transitively. For 2 points x and y, we take a trace decomposition x equals t transpose t and y equals s transpose s, where t and s are lower triangular matrix. Then y equals row A x with A equals st inverse. And this parameters, this Hessian domain is interpreted as a parameter space of the central normal distribution, central mean, so the mean is fixed to 0, and the covariance matrix differs in this case. And this is naturally identified with omega n as s equals 1 over 2. For other cases, so we need another family of distributions, so-called Wishart distributions. And this is not only the homogeneous, such G1/2 over GS is not only the homogeneous metric on the omega n. I mean, so we have many other homogeneous metrics on the same cone. Namely, so we have a parameter, so multi-parameter, so S1, Sn is positive numbers, then define so phi s, another potential function like this. So this is a linear combination of log determinant and log determinant xk is a lower upper left submatrix of this symmetric matrix. Then such function and let GS with the Hessian of this potential function. And for the previous case, so the G scalar S equals just in this case, so GSSSS. So this potential is not invariant for all row A, but if so A is lower triangular matrix, then the GS is invariant under this group. And this group of lower triangular matrices acts on the cone transitively, then GS is also homogeneous Hessian domain, a Hessian metric on the same domain omega n. And this GS exhausts all homogeneous Hessian metric. So every homogeneous Hessian domain on omega is isomorphic to such GS with so multi-parameter, and this parameter is unique. So if S is different, then the GS is not isomorphic. So in this way, so omega n, we can parameterize, we can determine all homogeneous Hessian domain, Hessian metric on the same cone omega n. The third example is the direct product of omega n and Rn. So the definition of GS is rather complicated, but the important thing is this is the potential function is given like this. So this is just the summation of the potential on the omega n and this quantity. Then this omega s, this metric GS is invariant under the following transformation sigma A and tau B, where A is GAN and B is Rn. And these transformations, by these transformations, any 2 points in UN can be mapped each other. So this GS is homogeneous Hessian metric on this space. And this space is interpreted as the parameter space of all normal distributions where mu goes around on Rn and sigma goes over the omega n. And this is identified with UN, and again for G 1/2. And for another S, we need the non-central Wishart distributions. Here, so we give another more convenient realization of the domain UN. Here, UN is omega n times Rn, but I realize this element like this. So Bn is the space of symmetric matrices of size n plus 1, but divided or taken a quotient by this En plus n1, n plus 1. So this means that the n plus 1 is the right bottom component is made as indefinite. Taking a quotient, then this component is indefinite. Then so I realize the element of UN as a set of positive definite matrix and vector like this. Then our automorphism group, automorphism action, here sigma A and tau B is described in very simple way. And for S, the multi-parameter version, we consider the phi S, the multi-parameter version of potential, and taking let GS be the Hessian of this phi S multi-parameter. Then GS is invariant under the same. So A is a lower triangle matrix, and tau B is just a vector. B is an arbitrary vector. Then, so we have the Hessian, homogeneous Hessian domain, or Hessian domain of UN, like this. And the this is important that this comes from the there's a parameter space of normal distributions. And this Hessian domain, UNGS, is not isomorphic to the direct product of Euclidean space. So the UN is by definition the direct product of Euclidean space and positive definite cone. But as a Hessian domain, it is not isomorphic. This is different Hessian domain. And my main result is every homogeneous Hessian domain is isomorphic to the intersection of this UN with an appropriate affine subspace gamma of Bn. Bn is this incomplete matrices and some appropriate parameter S, where the size of n can be taken to be less than or equal to the dimension of the domain of a homogeneous Hessian domain. So please see the proceedings for construction of this gamma and the set of matrices with specific block decomposition. I'm sorry, so here I just show example how we realize the two-dimensional homogeneous case. There exists 5 two-dimensional homogeneous Hessian domain, and I show the, how gamma looks like. And application of this main result is in future, so realization of homogeneous exponential families. Yes. So here is the example of my realizations. First, the Euclidean space into, so U2 is the 3 times 3 matrices with 3 components are indefinite. And we have, on U2, we have a homogeneous Hessian domain, a Hessian metric GS. And we take embedding from here to this matrix. Then, in this way, so Euclidean metric is induced from the ambient metric on U2. The second is the inner product of half, this product of 2 half lines. So x1, x2 positive, it's like this. And the third one is the direct product of R and half line, and it means just this. And actually, the image of these embedding is just the intersection of affine spaces, intersection of spaces of the matrices of such a specific form. So, in other words, so R2 is realized as the intersection of U2 with matrix of this form. R2 half is intersection of U2 with matrices of this form, something like this. This is rather too simple to say. And the fourth, the domain U1, so the product of positive line and real line, the metric is explicitly like this. And the fifth example is a parabolic domain. So originally this is defined as y is greater than x squared. So this is just a parabolic in the upper part of parabolic line. And let phi s the potential function s times this stuff. And second, taking a Hessian, we have this Riemannian metric. And this metric is invariant under these dilations and such translations. So we can check just directly using this expression, but probably so it is easy to investigate this how phi s behaves under these transformations. Anyway, the group, automorphism group, is generated by these transformations, and this transformation acts to this two-dimensional domain transitively. So any 2 points can be mapped by these transformations. So this GS is homogeneous. And we have the embedding from this y over y greater than x squared like this. So please see that the positive definiteness of this matrix 1xxy is just exactly y is greater than x squared. And the automorphism group is the dilations and translations can be described in this matrix multiplication like this. So we have this public domain is also realized in this specific domain with intersection of affine spaces of the matrices of these forms. And moreover, we can see, we can check by computation, but we can easily understand that this domain D and original U1 realized in this way are mutually dual. So it means that this mapped to each other by Legendre transform of potential functions. So for general realization of any homogeneous Hessian domain is more or less in the such case, such form. So every homogeneous domain is intersection as some affine subspace with this specific UN. And in proceedings, in the proceedings, I give some algebraic structure on the ambient space of U2, such that the intersection of UN with gamma is again homogeneous Hessian domain if and only if this gamma it has a subalgebra of this algebra structure of this ambient space. But please see the proceedings for the detail. Okay, thank you very much.